Hey guys, thanks for checking back and a short video clip. Topic geometries, molecular geometries, and how the outside electrons, of particular orbitals of atoms bonded together repel from each other and try just to get as far away from each other as possible. So the simplest scenario would be just two atoms bonded together. And, well, then it's just got to be what we call a linear molecule. Two atoms bonded together, doesn't matter if they're the same. This would be a non-polar bond, non-polar molecule. Let's see, what was I going to say? Oh yeah, purely covalent bond. But this, of course, different atoms, different elements. Polar bond, polar molecule. But that's not necessarily the topic of polarity. But I'm just saying, triple bond, double bond. You should be pretty comfortable with figuring out how we got these based on what we've been practicing so far. If not, rewind, go back, practice. What if three atoms are bonded together? Could be, of course, different elements, but or it could be the same element, like ozone or something. If there's no lone pairs on that central atom that's, the other two are focused around, then the molecule is again linear. It's 180 degrees. Sometimes double bonds, sometimes single bonds, but the most important thing would be that central atom has no lone pairs, which is kind of weird because there must be, if the central atom has its octet satisfied, then there must be some double bonding in there somewhere. Oh darn, I forgot a lone pair right there on the nitrogen. What do you know? There's a lone pair there. I should fix that before I PDF this. Often we'll pay attention to the bond angles. Of course, if it's linear, it has to be 180 degrees. Doesn't that look like some kind of silly alien smiley face? I'm easily amused, sorry. Alright, so what's the next possible scenario? What if we had three atoms bonded around a central atom instead of just two? Well, thinking in space, three-dimensionally, but it turns out this is flat anyway, right? The best way to get three things away from each other is to make them 120 degrees. 120, 120, 120, 120. That's 360 divided by 3. 120 degrees away from each other. This doesn't happen very often, but it can be, especially in the case of, well, because if this is one pair of shared electrons and that's another, that's 2, 4, 6. And boron is famous for being electron deficient and not quite getting its octet. 6 is not the octet. Too shy. So boron trifluoride, boron trihydride, boron trichloride, boron tri anything. 120, 120, 120. But that leaves the boron electron deficient, and looking for electrons, we call it an electrophile. So it could look for a lone pair somewhere to react with. Oh yeah, another scenario. Here's a carbonate ion with some resonances, not just here, not just here, not just here, but kind of that extra bond smeared around the whole thing. But the carbon has only 1, 2, 3 regions of electron density around it, so that, albeit a double bond in there, kind of smeared around. So we'll call that trigonal planar, triangle flat. Another example of a triangle flat molecule, SO2. SO2 molecule, a nasty gas, has enough to satisfy the octet on the sulfur. We're forced to do some extra bonding here. So, yeah, I apologize about that. Let's see. Oh yeah, so I got a lone pair on the sulfur. This is a resonance here between these two. Not flipping back and forth, kind of smeared amongst both of them. And the lone pair repels the bonding pairs even a little bit more than they repel each other. So instead of 120 like I had up here, I had 120, 120, 120, 120, 120, 120, 120, 120, 120, 120, 120 degrees. Here I'll have a little bit less than that if you care, but if you said 120, that'd be kosher, but technically it's a little bit less than that. Oh yeah, we call the molecule bent, even though the electron pair geometry is trigonal planar. triangle flat. The shape of the molecule, the molecular geometry, called bent. The most common, often, geometry is called tetrahedral because there are four things corresponding to the 2, 4, 6, 8 electrons of the octet around the central atom. The angle is 109.5. You should remember that. This would be carbon 4 hydrogens, so methane, or carbon tetrachloride, or carbon with anything around, any 4 electron densities around the carbon. We're going to call it tetrahedral, about that carbon. And the angle is 109-ish. Some famous twists on that. Let's put a lone pair on the central atom. This is still tetrahedral, but tetrahedral electron pair geometry, but now the shape of the molecule, we call it triangle pyramid. So if this and this are in the plane of the paper, this one's coming out towards you and this one's going behind the screen. So yeah, it's three-dimensional. Get yourself some models and play with it if you can't see the three-dimensionality. Yeah, so it's triangle pyramid. But let's take another one of those lone pairs and stick it on the central atom. Oh, by the way, so if this was 109, then that lone pair pushes these bonding pairs a little bit closer than they usually would be. We could call it 107 to be technical about it. Let's put another lone pair on the central atom and we get water or something like it. So if this lone pair and this lone pair are in this plane of the screen, this hydrogen bonding pair and this hydrogen bonding pair is going in front and in back of the screen. That's usually what those little symbols mean. That comes out towards you and that goes behind the screen. It's our best attempt at drawing this three-dimensional object on a flat screen. Yeah, and if this was 120, 120, no, 109, 109, 109, 109, now two lone pairs actually repel each other even more and repel the bonding pairs down to something a little bit closer even. It's called a bent molecule. The electron pair geometry is tetrahedral, but the angle's 105. Let's go to trigonal bipyramidal. So now we're expanding our octet, and the central atom has 2, 4, 6, 8, 10. The angle between the vertical off the plane and the plane is 90 degrees, but the angle between any two electron densities in the plane, 120 degrees. So, can you imagine that? Have you seen this model in class? Get some gumdrops and toothpicks and play with it yourself if you like. But that's the story. Remember that electron pair geometry is called trigonal bipyramidal. Oh yeah, I see the triangle and the double pyramid because I got a pyramid up here and a pyramid down here. Here's an example of trigonal bipyramidal. Phosphorus pentachloride. What if I took off one of those bonding pairs and made it a lone pair? And I would prefer to put it here. And if you didn't put it there, then the molecule would know it should repel more. This lone pair repels more than the bonding pairs, and so everything else kind of arrange themselves into what we call a seesaw. Yeah, if this were the vertex or the fulcrum of the teeter-totter, then this and this would go. But seesaw. What if I put another lone pair? Oh yeah, where would it go? Would it go up here? Would it go down here? Would it go over here? We want to put that addition to the next lone pair in a position to get as far away from the other lone pair as possible. And so it ends up looking like this, T-shaped. This and this are 120 from each other, also about 120 from this, and 90 from that. And that's the best way to get those lone pairs as far away from each other as possible. Put another lone pair on, and it goes again on the plane, so that the lone pairs are 120 degrees from each other, and it's linear. So this now is 180 degrees, across from each other. Shape of the molecule is linear, but the electron pair geometry is still trigonal bipyramidal. And lastly, what about the octahedron? Expand the octet one more time. The central sulfur, or central phosphorus, or selenium, or something, larger than that in the non-metal available d orbitals to bond to expand the octet with. Now these are all 90 degrees. They're all equivalent to each other. 90, 90, 90, 90, 90, 90. Octahedron. Oh my goodness. Oh, I forgot my bromine lone pairs right there. So, what am I doing? I'll fix that. Selenium hexabromide. Could be, don't know how stable it is. Take one of the bonding pairs, replace it with a lone pair. Doesn't matter which one in this case. Call it this one, and you get a square pyramid molecular geometry, still octahedral, or you could call it square bipyramidal, but it's always called octahedral. Make one of the, which one of these bonding pairs, if you had to replace it with a lone pair, would be the most stable configuration to get those lone pairs away from each other? Yeah, try that. Make it a square planar molecule where the lone pairs are opposite each other. And yeah. What about another one? Well, let's put it right there. Doesn't really matter now. T-shaped. And another one. Doesn't really matter, but let's make them as far away from each other as possible. So dot 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 dot, and again back to linear. And so it's a linear molecule, but still octahedral electron pair geometry. So there's the two geometries to consider, but oftentimes we'll ask the geometry of the molecule. Oh, that's it. Thanks, guys. Maybe get some models or gumdrops and toothpicks if we need to. Many of you guys are good spatial thinkers. You can Google it and get images of these molecules without really going to the expense of buying a molecular model. See you in class.